The universe is the grandest of all subjects, the totality of everything that exists. Space and time, matter and energy, the seen and the unseen, the known and the still undiscovered. To speak of it is to step into a realm of near-limitless scale, where distances stretch across billions of light years, where time is measured in billions of years, and where the tiniest particles and the largest structures are bound together by the same laws. It encompasses galaxies by the trillions, stars beyond numbering, and perhaps even more planets than stars, yet also the invisible fabric of dark matter and dark energy that shape its fate. The universe is both intimate and remote, for while it contains the most distant galaxies shining from the edge of visibility, it also resides within us. The atoms of our bodies forged in the cores of ancient stars. To introduce the universe is to admit that no description can exhaust it, but every attempt opens a door into wonder, reminding us that we live not apart from it, but entirely within it. To say that the universe is 13.8 billion years old is to stretch human imagination to its very limits. We live our lives on scales of days, years, and perhaps decades. A century already feels immense when measured against the brevity of human existence. 1,000 years, the span of empires and civilizations, is a distance of time that requires effort to grasp. But when we speak of billions of years, we leave behind the familiar rhythms of history and enter into the strange vastness of cosmic time. 13.8 billion years is not merely a number. It is the age of everything we know, the measure of the journey from the first flash of light to the present moment in which we breathe. To say the universe is this old is to speak of a story so long that our minds can only glimpse fragments of its scale, like shadows cast on the wall of a cavern too vast to comprehend in its entirety. The age is not a guess pulled from wonder or imagination, but the outcome of careful observation. Astronomers trace the faint glow of the cosmic microwave background, the afterlight of the Big Bang, a radiation stretched thin across the cosmos like an ancient whisper still echoing. They measure the expansion of the universe itself, the way galaxies drift apart in patterns that reveal the underlying tempo of cosmic growth. By studying the oldest star clusters, the dimmest remnants of the early universe, scientists converge on the same figure, about 13.8 billion years. It is an age with remarkable precision, one that tells us that the universe is not eternal in the way our ancestors once thought, but that it had a beginning, a birth out of fire and energy, a moment from which time itself has flowed. This age sets boundaries on everything we see. The oldest light we can detect comes from that first flood, released just 380,000 years after the Big Bang, still traveling to us today. The galaxies we study are snapshots from earlier and earlier times, as though telescopes were not machines of magnification but of time travel, letting us peer back toward the beginning. No matter how far we look, we cannot see farther back than the age of the universe itself, for there was no before in any ordinary sense. Time began then, space began then, the very fabric in which all things unfold took shape in that first instant. 13.8 billion years is not simply a measurement. It is the age of time itself, the measure of existence's unfolding. Placed against this backdrop, human history is almost invisible. Our species has existed for roughly 300,000 years, a flicker compared to cosmic epochs. Civilization has written records stretching back perhaps 5,000 years. The stories we tell, the monuments we build, the wars we wage, all unfold in a fragment so small it is hard to place on the cosmic scale at all. If the entire history of the universe were compressed into a single calendar year, the Big Bang exploding into existence on January 1st, then the Earth would not form until September, dinosaurs would rise in late December, and all of human history would unfold in the final seconds before midnight on New Year's Eve. To realize this is both humbling and clarifying. We are latecomers, arriving after a long and ancient unfolding, inhabiting a cosmos whose age dwarfs our personal and collective scales of meaning. Yet the age of the universe also carries a kind of comfort. The fact that it has endured for 13.8 billion years suggests a patience and stability that can outlast our anxieties. We often imagine the universe as fragile because our lives are fragile, but the cosmos itself is resilient, a vast continuity in which stars are born and die, galaxies merge, and still the whole persists. To know the age of the universe is to feel the presence of something that has weathered eons beyond reckoning. It reminds us that our lives, though brief, are part of something enduring, woven into a story that began long before us and will continue long after. There is also beauty in the thought that everything we are comes from this long history. The carbon in our bodies, the oxygen we breathe, the iron in our blood. All were forged in stars that lived and died billions of years before our sun was born. We carry within us the memory of that vast age, atoms that have traveled through time across eons. 13.8 billion years is not simply an abstract number written in scientific texts. It is inscribed in the matter of our own being. Each of us is a late expression of a story that began with the Big Bang and passed through the long labor of stars. We are the children of time itself, shaped by an age that we can barely imagine. And yet, even as we grasp this number, it is not final. The age of the universe tells us how long it has existed, but not how long it will endure. The same science that measures its age also tells us of its future, a future in which expansion continues, stars exhaust their fuel, galaxies drift farther apart, and time stretches into darkness. To live at this moment in the universe's 13.8 billion year history is to live in a luminous age, when stars still shine, when galaxies are still close enough to be seen, when life can still arise on planets warmed by suns. It is a rare and precious window, a brief flowering in the long chronology of the cosmos. To speak of the universe as 13.8 billion years old is, in the end, to confess both awe and limitation. Our words stumble at the edge of such magnitude, and yet we reach for them because we must. The number is not meant to be held comfortably in the mind. It is meant to remind us of the immensity into which we are born, the ancientness from which we arise, and the astonishing fact that in this very moment, after so many billions of years, the universe has given rise to eyes that can look back and wonder at its age. To stand on a shoreline is to feel the immensity of number. The eye can take in only a small patch of sand, and yet even that patch is uncountable, a scattering of grains so fine that they slip between fingers, impossible to keep track of. Walk a little farther, and the same view extends endlessly, dune after dune, beach after beach, each filled with more grains than the mind can hold. And yet science tells us that the stars outnumber even these. Not just the stars we can see on a clear night, which are already too many to name, but the stars across the galaxies in clusters and filaments that stretch to the very edges of observation. There are more stars than grains of sand on all the beaches of Earth combined. It is a statement that almost collapses under its own weight, for the mind reaches a point where numbers dissolve into pure astonishment. The comparison is not a poet's exaggeration. Astronomers have tried, with careful methods, to estimate. The grains of sand are easier, in a sense, to reckon. One can measure the average volume of a grain, calculate the area of the world's coastlines, and multiply by depth, arriving at figures that stagger the imagination but still remain finite, perhaps on the order of 10 to the power of 18 grains. For the stars, the task is more subtle. Our galaxy, the Milky Way, contains on the order of 100 billion to 400 billion stars. And the observable universe contains at least 2 trillion galaxies, scattered across space. When the multiplication is done, the total rises to numbers so vast that ordinary language ceases to serve. There may be a sextillion stars or more, a 1 followed by 21 zeros, greater by far than the number of sands on our planet's shores. What begins as a poetic comparison ends as a sober fact, anchored by observation and calculation. Yet the true significance of this fact is not in the digits themselves, but in the imaginative pressure they exert. When we hear that stars outnumber grains of sand, we are forced to expand our sense of scale. A single beach is already overwhelming to the senses. To add another, and then another circling the globe, is to confront abundance on a level that seems inexhaustible. And then, suddenly, that abundance is made small, overshadowed by the sky itself. Every speck of sand becomes a metaphor for a blazing sun, with its own planets, its own possibilities. The immensity of the cosmos is not abstract, but tangible because it is measured against something we know. We have felt sand, held it in our hands, brushed it from our feet. To realize that stars surpass even this most familiar symbol of countlessness is to feel the reach of the universe pressing in. There is also a kind of humility in the comparison. The beaches of Earth are only a thin covering, a delicate skin on the planet's surface. The stars, by contrast, compose the very fabric of the cosmos. To be told that the stars outnumber the grains of sand is to realize that what seems abundant to us is still only a shadow of the universe's greater abundance. It pulls us out of the illusion that what is large in our experience is large in itself. Our senses are provincial. They teach us that the beach is infinite when it is not, that the sea is endless when it is not, that the sky of visible stars is the universe when it is only the faintest slice. To be corrected by the stars is to be reminded that human perspective is always partial, always humbled by what lies beyond. And yet, if we dwell on it longer, the fact is not only humbling but exhilarating. For each star is not merely a number, but a furnace of light and matter. Each may be accompanied by planets, perhaps many worlds orbiting quietly in the dark, each with its own weather, geology, and perhaps even life. If stars are more numerous than sand, then so too might be the worlds, the possible cradles of existence. The multiplication of stars is also the multiplication of possibility. The comparison with sand reminds us not only of immensity but of fecundity, of a universe that offers more than we could ever hope to explore, more than we could even imagine. On the human scale, this immensity can feel isolating. To imagine stars beyond sand is to realize how small a thing we are, how tiny our history, how fragile our moment in time. A single grain of sand is negligible, swept by the tide, unnoticed. To think of ourselves as one among more stars than sand is to feel our smallness almost to the point of invisibility. But invisibility does not mean meaninglessness. A single grain, though lost among trillions, still exists, still carries weight and texture. Likewise, we, though one small species on one small planet, are part of the greater abundance. Our existence participates in the same immensity that dwarfs us. The recognition of scale can shrink the ego, but it can also expand the sense of belonging. Perhaps that is the final gift of the comparison. It is not meant to terrify but to open. When we hold a handful of sand, we can remember that each tiny grain has its counterpart in the night sky and beyond. When we look up and see only a few hundred stars with the naked eye, we can remember that the visible is only a doorway into the invisible multitude. We are surrounded, in every direction, by a cosmos that defies our arithmetic. To know that the stars surpass the sands is to live in a world more plentiful, more radiant, and more astonishing than our ancestors ever guessed. It is to stand at the edge of the sea, watch the waves, and know that what lies above us is greater still. Venus, the second planet from the Sun and Earth's closest planetary neighbor, is a world of extremes and paradoxes. It is nearly the same size and mass as Earth, often called its twin, yet the similarities end there. Its atmosphere is a choking shroud of carbon dioxide, its surface hot enough to melt lead, and its clouds laced with sulfuric acid. But perhaps the strangest fact of all is hidden not in its toxic skies or blistering heat, but in its sense of time. On Venus, a single day, the time it takes the planet to rotate once on its axis, is longer than an entire year, the time it takes to complete one orbit around the Sun. This counterintuitive truth is one of the most remarkable features of our solar system and reveals much about the peculiar nature and history of this enigmatic planet. A planet's day and year are governed by two different motions, rotation and revolution. Rotation is the spin of a planet on its axis, the motion that brings sunrise and sunset. Revolution is the path it takes around the Sun. On Earth, we rotate once every 24 hours, producing our day, and revolve once every 365 days, creating our year. Most planets follow a similar pattern. They spin quickly compared to the time it takes to orbit the Sun. But Venus defies this pattern dramatically. It takes about 243 Earth days to complete one full rotation on its axis, and only about 225 Earth days to make one trip around the Sun. This means that a single day on Venus lasts longer than its entire year. As if that were not strange enough, Venus spins in the opposite direction from most other planets, including Earth. While Earth and most planets rotate counterclockwise when viewed from above their north poles, a motion called prograde rotation, Venus rotates clockwise, a motion known as retrograde rotation. On Venus, the Sun rises in the west and sets in the east. Its slow, backward spin means that if you could stand on the planet's scorching surface and somehow survive, you would see the Sun crawl across the sky in the wrong direction, taking months to complete its journey from horizon to horizon. The reasons for Venus's peculiar rotation are still debated, but astronomers have proposed several theories. One possibility is that early in its history, Venus was struck by a massive object, an impact powerful enough to slow and reverse its spin. Another idea suggests that the thick atmosphere of Venus, combined with gravitational interactions with the Sun, gradually altered its rotation over billions of years. Venus's dense air moves around the planet far faster than the surface spins, creating a phenomenon called superrotation. This intense atmospheric drag, combined with tidal forces from the Sun, could have contributed to the planet's sluggish and retrograde motion. Whatever the cause, Venus's unusual day is a relic of its chaotic past and the complex interplay of forces that shaped its evolution. The length of a Venusian day has curious consequences for the planet's environment. Because the Sun appears to move so slowly across the sky, one side of Venus remains in sunlight for months while the other endures a long, drawn-out night. Yet despite this extreme difference in day length, the surface temperature is remarkably uniform across the planet. That is because Venus's thick atmosphere acts like an enormous insulating blanket, trapping heat through a runaway greenhouse effect and distributing it evenly. Day or night, equator or pole, the surface temperature hovers around 465 degrees Celsius. A scorching environment that erases the usual temperature contrast seen on planets with thinner atmospheres and shorter days. The long day also influences how we measure time on Venus. There are two ways to define a day. The sidereal day, which is the time it takes for a planet to complete one rotation relative to the stars, and the solar day, which is the time between two noons, the period from when the Sun is highest in the sky to when it reaches that point again. On Venus, the solar day is even longer than the sidereal day, about 117 Earth days. That means that from sunrise to sunrise, nearly 4 months pass. A Venusian day in the sense of daylight and darkness is thus about half the length of its year. This strange relationship between day and year makes Venus a world that challenges our intuitive understanding of time. On Earth, days are brief compared to the slow sweep of a year. Seasons come and go many times before a planet completes its orbit. On Venus, the rhythm of time is reversed. A year passes more quickly than a single rotation, and the concept of morning and evening stretches far beyond anything we experience on Earth. If humans were ever to walk on Venus, a feat far beyond our current capabilities, they would witness a sky where the sun rises only once or twice during an entire year. The fact that a day on Venus is longer than its year is more than just an astronomical curiosity. It is a window into the violent history and dynamic nature of planets, a reminder that the solar system is not governed by simple patterns but shaped by collisions, tidal forces, and the slow sculpting of time. It shows that planets, even those born as siblings, can evolve into radically different worlds. Earth spins briskly and teems with life. Venus turns slowly under crushing pressure and searing heat. Two worlds that began alike now stand as opposites. One a cradle, the other a furnace. In the end, Venus's strange sense of time is part of what makes it so fascinating. It is a planet that defies expectations, where familiar ideas about days and years dissolve under alien skies. Its slow, backward rotation and inverted day-year cycle reveal a universe more complex and surprising than we might imagine. In the deep silence of Venus's atmosphere, where sunlight drifts lazily across the horizon over months, time itself seems to stretch and twist. A cosmic reminder that even the most basic rhythms we take for granted are not universal, but shaped by the unique stories of worlds beyond our own. When we look into the night sky, it is tempting to believe that what we see is the universe itself. The stars glittering across the dark, the faint haze of the Milky Way, the occasional planet shining with a steady light. Yet science tells us that what we can see with our eyes, or even with the most powerful telescopes, is only a fraction of reality. The overwhelming majority of the universe is invisible, composed of forms of matter and energy that do not shine, do not absorb, do not reflect in any way that our senses can detect. What we call the visible universe is, in truth, a tiny scrap of the whole, like the crest of a wave rising above the surface while the great depth of the ocean remains concealed beneath. The cosmos is mostly hidden, and we live surrounded by mysteries our sight cannot touch. The discovery of this fact is one of the most unsettling revelations of modern cosmology. For centuries, humanity assumed that the stars, galaxies, and nebulae that could be observed represented the fullness of what exists. Telescopes extended our reach, revealing countless more galaxies than we had ever imagined. But they too seem to suggest that what can be seen is the essence of the cosmos. Only in the last century did evidence accumulate that something far larger lurks beyond the limits of vision. Galaxies spin too quickly, their stars moving in ways that visible matter cannot explain. Clusters of galaxies hold together with a gravity that far outweighs the mass we can observe. The universe itself expands in a way that suggests the presence of a hidden energy pressing space apart. When the sums are done, the conclusion is inescapable. All the stars, planets, gas clouds, and luminous objects we see amount to less than 5% of the cosmos. The rest is invisible, dark matter and dark energy, names that signify not understanding but mystery. Dark matter, though unseen, reveals itself through its pull. It is like a ghostly scaffold, a hidden framework within which galaxies form and move. Without it, the visible universe would not hold together. The stars we admire would scatter into the void. We know it is there, but we do not know what it is. Perhaps it is made of exotic particles never encountered in earthly experiments, perhaps something stranger still. It neither emits nor absorbs light, remaining forever in the shadows. And yet it outweighs all the luminous matter by more than 5 to 1. The universe we see is balanced, carried, and shaped by this invisible mass. What we think of as the main stage is in truth a set of faint props lit by the unseen. Stranger still is dark energy, which does not merely pull but pushes. In the late 20th century, astronomers discovered that the universe's expansion is accelerating, as though some hidden pressure is stretching space itself apart. This repulsive force accounts for nearly 70% of the universe's total content. And yet we do not know its nature. We call it energy because it behaves like one, but it remains opaque, unmeasurable except through its effect on the cosmos at large. It permeates every corner of space, filling the void with a presence we cannot see or touch. To admit its existence is to admit that most of the universe is made of something we can neither imagine nor describe. The invisibility of the universe is not only a scientific puzzle but a philosophical challenge. For most of human history, sight has been treated as the highest of senses, the one that reveals truth. To see is to know. Yet here we find that sight misleads us, showing only the surface of things while hiding the depths. The stars we admire are not the full truth but merely the luminous decoration of a much larger, hidden structure. Reality is woven not of what we see but of what we cannot see, and this forces us to reconsider the relationship between knowledge and perception. Perhaps the deepest truths are always like this, felt through their effects rather than directly observed, known through inference rather than vision. At first, the thought that most of the universe is invisible may feel unsettling. We are used to equating the visible with the real, and to learn that the real extends so far beyond the visible threatens to shrink our confidence. But there is also wonder here. The cosmos is richer, stranger, and more abundant than the naked eye could ever reveal. To know that most of the universe is hidden is to realize that mystery itself is part of the fabric of existence. The darkness is not emptiness, but fullness beyond comprehension. We are surrounded by presences that act upon us, hold our galaxies together, shape the destiny of the cosmos, and yet remain unseen. To live in such a universe is to live in a place that continually exceeds us, that resists our desire to reduce it to simple clarity. Perhaps this recognition offers a lesson beyond science. We are reminded that what we perceive is never the whole, whether in the cosmos or in life. The visible is only one layer of truth. Just as galaxies depend on unseen matter and energy, so too our daily lives may depend on hidden forces, relationships, histories, ideas, or emotions that shape outcomes without revealing themselves in plain sight. To acknowledge the invisible is to acknowledge that reality is always deeper than appearances. It is a lesson in humility, but also in openness. So when we look into the night sky and see its scattered points of light, we should remember that we are looking at less than 5% of what exists. The rest lies concealed, silent yet powerful, a reminder that the universe is not transparent but veiled. And in that veil lies its greatest wonder. Not only what is revealed to our eyes, but the vast invisible depth that sustains it all. In the vastness of the cosmos, where temperatures can soar to unimaginable extremes near blazing stars, or inside the hearts of galaxies, there exists a place so cold that it defies intuition. It is colder than the darkest voids between galaxies, colder than the faint background glow left over from the birth of the universe itself. This place is the Boomerang Nebula, a faint, ghostly cloud of gas and dust drifting some 5,000 light-years away in the constellation Centaurus. Astronomers have measured its temperature at just 1 Kelvin above absolute zero, about -272 degrees Celsius, making it the coldest known natural location in the entire universe. The Boomerang Nebula is not a nebula in the traditional sense of a stellar nursery where new stars ignite from collapsing clouds. Instead, it is the dying breath of a star that once shone like our sun near the end of its life. This aging star exhausted the nuclear fuel in its core, causing its outer layers to swell and drift into space. In most such cases, the result is a planetary nebula, a glowing shell of gas gently expanding away from its parent star. But in the Boomerang Nebula, something more dramatic is happening. The central star is losing its mass at an extraordinary rate, and the gas is streaming outward at speeds exceeding 160 kilometers per second. This violent outflow creates conditions unlike anywhere else we know. The reason the Boomerang Nebula is so cold lies in the physics of expansion. As a gas expands rapidly into a vacuum, it cools. This is the same principle that causes compressed air released from a canister to feel icy to the touch. In the Boomerang Nebula, the gas ejected from the dying star is expanding so quickly that it cools far below the 2.7 Kelvin temperature of the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills the universe. No other natural process observed in space cools material this much. The nebula's interior plunges to about 1 Kelvin, just a fraction of a degree above absolute zero, the temperature at which atomic motion nearly ceases altogether. Seen through telescopes, the Boomerang Nebula is as beautiful as it is strange. Early radio observations in the 1990s revealed its frigid temperature, but it was the Hubble Space Telescope that unveiled its striking shape. Instead of the simple hourglass shape astronomers expected, the nebula appeared as a delicate, double-lobed cloud, glowing faintly in scattered starlight. Its ethereal form, shaped by stellar winds and the geometry of the outflowing gas, inspired its name, the Boomerang Nebula. Some have likened its shape to a bow tie or butterfly, but its ghostly symmetry hints at the underlying violence that created it. What is perhaps most remarkable is that this extraordinary cold exists in a universe where absolute 0 Kelvin is a physical limit that cannot be reached. The cosmic microwave background sets a natural temperature floor across space. Even in the most remote cosmic voids, the universe is bathed in this faint relic radiation. Yet the Boomerang Nebula, by virtue of its explosive expansion, manages to dip below this universal temperature baseline. In a sense, it is colder than the universe itself, a paradoxical pocket of extreme chill forged by a dying star's final outburst. The Boomerang Nebula also offers astronomers a fleeting glimpse of a brief and little understood phase in stellar evolution. The violent outflow driving its intense cooling will not last forever. As the star continues to shed its layers, the gas will eventually slow and warm. The nebula will likely evolve into a more typical planetary nebula, glowing brightly as ultraviolet radiation from the exposed stellar core ionizes the surrounding gas. But for now, it remains in a transitional state, a preplanetary nebula, caught between the red giant it once was and the white dwarf it will one day become. Its extreme conditions also make the Boomerang Nebula a natural laboratory for studying the behavior of matter near absolute zero, albeit on a cosmic scale. Here, molecules and dust grains form and evolve in ways that cannot be replicated easily on Earth. Astronomers use observations across multiple wavelengths, radio, infrared, and visible light, to piece together the chemical and physical processes at work in this frigid environment. What they learn could illuminate not only the final stages of stellar evolution but also the origins of complex molecules that seed new solar systems. The Boomerang Nebula reminds us that the universe is full of extremes, places that defy our expectations and challenge our understanding of physical laws. It is astonishing to think that a dying star, once a source of light and heat, could create the coldest known place in existence. Yet this paradox underscores the universe's complexity. Death begets new phenomena, and endings often harbor the seeds of beginnings. The star's violent shedding of its outer layers, while signaling its demise, also sets the stage for the formation of new cosmic structures and perhaps, in time, new worlds. In the grand tapestry of the cosmos, the Boomerang Nebula is but a small and fleeting feature, destined to change as its central star continues its slow transformation. But for now, it stands as a record holder, a cosmic curiosity colder than any known natural environment. Its ghostly lobes drift silently in the darkness, an icy monument to the strange beauty of stellar death. And somewhere within that frozen expanse, Amid swirling clouds colder than deep space itself, lies the quiet heartbeat of a dying star, still shaping the universe in its final act. We move through the universe believing we understand its shape. We speak of length, width, and height, and we sense the passage of time as a fourth dimension. These four dimensions define everything we experience, from the fall of an apple to the motion of galaxies. Yet modern physics suggests that this familiar picture might be incomplete. The universe may have more dimensions than we can see, hidden layers of reality folded beyond our perception, shaping the cosmos in ways we barely begin to grasp. The idea that the universe could contain extra dimensions arises naturally from our attempts to unify the fundamental forces of nature. Gravity, electromagnetism, and the strong and weak nuclear forces each govern the behavior of matter and energy, but they are described by different theories. Physicists have long sought a single framework that explains them all. In the 20th century, this search led to the development of string theory, a bold and elegant idea that suggests that the basic building blocks of the universe are not point-like particles but tiny, vibrating strings. The vibration patterns of these strings give rise to the particles and forces we observe, much like different vibrations of a violin string produce different notes. But for string theory to work mathematically, the universe must have more than 4 dimensions. Most versions require 10 or even 11 dimensions to remain consistent. The 3 dimensions of space and 1 of time that we know are just part of a richer geometric structure. The additional dimensions are thought to be compactified, curled up so tightly that they are invisible to us, like tiny loops woven into the fabric of space itself. If they exist, they may be smaller than an atomic nucleus, hidden beyond the reach of even our most powerful instruments. This notion is not as strange as it may first seem. We are limited by our senses, and what we experience is only a fraction of reality. Imagine a two-dimensional being living on the surface of a sheet of paper. To that being, the universe has only length and width. The concept of up and down would be unimaginable. Yet we, existing in 3 dimensions, see the sheet from above and below as well. Similarly, we might be confined to perceiving only 3 dimensions of space, while others lie beyond our direct experience. If these hidden dimensions exist, they may not be merely mathematical curiosities. They could explain some of the universe's most profound mysteries. One such mystery is gravity. Compared with the other fundamental forces, gravity is astonishingly weak, billions of times weaker than electromagnetism. One possible reason is that gravity may be spreading into extra dimensions that we cannot see, diluting its strength in the 3-dimensional space we inhabit. Experiments with high-energy particle collisions and precise measurements of gravity at tiny scales are searching for evidence of such leakage. If found, it would revolutionize our understanding of the universe. Extra dimensions also play a role in theories of cosmology. Some physicists suggest that our universe may be a 3-dimensional brane, floating within a higher dimensional space known as the bulk. Other branes may exist alongside ours, perhaps even containing their own universes, separated from us by imperceptible gaps in higher dimensions. In this view, the Big Bang might not have been the beginning of everything but rather the result of 2 branes colliding, releasing enormous energy and creating the universe as we know it. The possibility of more dimensions also reshapes how we think about space and time themselves. In the framework of general relativity, gravity arises from the curvature of spacetime caused by mass and energy. If additional dimensions exist, the geometry of the universe could be far more complex than Einstein imagined. The shape and size of these hidden dimensions could influence the properties of fundamental particles, the behavior of forces, and even the evolution of the cosmos. The universe's deep structure might be like a vast, multidimensional tapestry, of which we see only a thin slice. Detecting these extra dimensions is one of the greatest challenges in physics. Because they may be curled up at scales far smaller than we can probe, direct observation is extremely difficult. However, physicists look for indirect signs. Tiny deviations from Newton's law of gravity at very short distances could hint at hidden dimensions. High-energy collisions in particle accelerators like the Large Hadron Collider might reveal new particles or phenomena that betray the presence of extradimensional space. Even the cosmic microwave background, the ancient afterglow of the Big Bang, could contain subtle imprints of dimensions beyond the familiar four. The idea that the universe may have more dimensions than we perceive is humbling and profound. It suggests that reality is far richer than our senses reveal, that what we experience as space and time might be just a shadow of a deeper structure. Throughout history, humanity's understanding of the cosmos has grown as we learned to see beyond appearances. We once believed Earth was the center of the universe, then discovered it was a small planet orbiting an ordinary star. We thought the Milky Way contained all the stars, only to find countless galaxies beyond it. Perhaps the next great leap is realizing that even the dimensions we inhabit are not the whole story. Whether these hidden dimensions are ever detected or remain theoretical, they remind us that the universe is stranger and more intricate than we imagine. Our world may be woven from threads we cannot yet see, shaped by spaces that curl beyond our reach. Somewhere, deep within the structure of reality, those hidden dimensions may hold the answers to questions we have yet to ask, about the origin of forces, the nature of matter, and the true architecture of the cosmos itself. And as we continue to explore, we may find that what we call the universe is only part of a much larger and more mysterious multidimensional reality. Across the vastness of the cosmos, where stars are born in clouds of dust and galaxies drift through the dark like islands of light, there is one thing that races faster than anything else: light. It is the ultimate speed limit of the universe, the swiftest traveler known to science, moving through the vacuum of space at about 299,792 kilometers per second. In just 1 second, a beam of light could circle Earth more than 7 times. In 8 minutes, it crosses the 150 million kilometers between the Sun and our planet. Nothing, no particle, signal, or force can outrun it. Light speed is not just a number. It is a fundamental property of the universe, woven into the very fabric of space and time, shaping how reality itself behaves. Light is more than what we see with our eyes. It is a form of electromagnetic radiation, part of a vast spectrum that includes radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. All of these move at the same incredible speed in a vacuum, regardless of their energy or wavelength. Whether it's the warm glow of sunlight, the invisible pulse of a Wi-Fi signal, or the deadly beam of a gamma-ray burst, they all travel at nature's ultimate pace. This universality makes the speed of light a cornerstone of physics, a constant that underpins the laws of the cosmos. For much of human history, people assumed that light's motion was instantaneous. It was too fast to measure with the tools of ancient times. But in the 17th century, astronomers like Ole Romer began to realize that light had a finite speed. Romer noticed that the eclipses of Jupiter's moon Io occurred slightly earlier or later depending on Earth's distance from Jupiter, and he concluded that the difference was caused by light's travel time. Later experiments refined the value, and by the 20th century, scientists had measured it with extraordinary precision. Today, the speed of light is not just measured, it defines the meter itself, the fundamental unit of distance. Albert Einstein placed light at the heart of his theory of relativity, which transformed our understanding of space and time. One of Einstein's key insights was that the speed of light in a vacuum is the same for all observers, no matter how fast they are moving. This idea shattered classical notions of absolute space and time. It meant that space and time are not rigid backgrounds but flexible dimensions that adjust to keep light's speed constant. Time can slow down and lengths can contract for objects moving near light speed, effects that have been confirmed by countless experiments. Light is the cosmic yardstick, the fixed point around which the universe's structure is built. The reason nothing can travel faster than light lies in the very fabric of physics. As an object with mass accelerates toward light speed, its energy, and therefore its effective mass, increases dramatically. To reach the speed of light itself would require infinite energy, something no known force or technology can supply. Light, on the other hand, has no rest mass. It is made of photons, particles that always move at light speed and cannot exist at rest. This unique property allows them to be the swift messengers of the cosmos, racing across billions of light-years to deliver images of galaxies as they were in the distant past. Light's unmatched speed shapes everything we know about the universe. Because it takes time for light to travel, looking into space is also looking back in time. The light from the sun shows us our star as it was 8 minutes ago. The light from the nearest star, Proxima Centauri, left more than 4 years ago. When we observe galaxies billions of light-years away, we are seeing them as they were billions of years in the past, long before Earth even formed. The finite speed of light turns telescopes into time machines, revealing the universe's history written in beams that have crossed unimaginable distances. Even though nothing can outrun light, scientists continue to test the limits of this cosmic rule. Some experiments have produced particles that seem to travel faster than light in certain materials, but these effects do not break the fundamental limit in a vacuum. Others explore the strange realm of quantum mechanics, where entangled particles influence each other instantaneously across space. Yet even these phenomena do not transmit information faster than light. They do not allow messages or objects to exceed the universal speed barrier. Light's supremacy remains unchallenged. The speed of light also defines the scale of cosmic distances. Astronomers measure space in light-years, the distance light travels in a year, about 9.46 trillion kilometers. When they say a galaxy is 10 million light-years away, they mean that its light has been traveling toward us for 10 million years. This way of measuring connects space and time into a single continuum, reflecting how deeply light is woven into the structure of the cosmos. There is a poetic dimension to light's speed as well. Connects the smallest moments to the vastest scales. It is the reason we see stars twinkle, the reason sunsets glow red, the reason we can communicate instantly across oceans with radio waves. It binds our understanding of nature, linking the physics of atoms to the motion of galaxies. It is both a physical reality and a symbol of the universe's limits, a reminder that even in the vast expanse of space, there are boundaries that cannot be crossed. In the end, light is more than just the fastest thing in the universe. It is a cosmic law, a bridge between past and present, a constant that shapes the flow of time itself. Every photon racing through the void is a messenger from somewhere and someone, a bearer of stories written across space and time. Its speed is not just a number on a page. It is the heartbeat of the universe, the rhythm by which reality unfolds. And as long as the cosmos endures, nothing will ever outpace it. To say that black holes can slow down time is to step into a realm where the familiar rules of existence bend and twist. In everyday life, time feels like the most stable of things, flowing steadily from past to future, unbending in its rhythm. A second is always a second. An hour passes at the same rate whether we are awake or asleep. But Einstein's theory of relativity taught us that time is not absolute. It is woven together with space into a fabric that curves and stretches under the influence of gravity. The stronger the gravity, the slower time flows compared to regions of weaker gravity. Near a black hole where gravity reaches its most extreme, this effect becomes astonishing. Time itself dilates, slowing to a crawl when viewed from afar. What seems a few moments to someone falling toward a black hole may appear as centuries, millennia, or even eternity to someone watching from a safe distance. A black hole is born when matter collapses under its own weight, compressing into a singularity, a point of infinite density surrounded by an event horizon beyond which nothing, not even light, can escape. The event horizon marks the boundary where gravity becomes so absolute that spacetime itself caves inward. Here, the warping of time is so intense that an outside observer will never actually see an object cross the horizon. Instead, the object seems to freeze, slowing down more and more as time stretches toward infinity. Light from the falling object becomes increasingly redshifted, losing energy, until it fades away completely. To the outside universe, the object never falls in, it hovers forever on the threshold, arrested by the distortion of time. For the one who falls, however, time continues normally. Seconds remain seconds. The beating of the heart feels steady. Thoughts flow without disruption. This is the paradox of relativity. Time does not slow for the one experiencing it, but only relative to others in different conditions. To fall into a black hole would feel, from the perspective of the traveler, like any other journey, until the immense tidal forces ripped the body apart. But to the outside observer, that same traveler would appear to move more and more slowly, stretched out into eternity, never quite reaching the horizon. Two realities coexist, each true from its own vantage. This slowing of time near black holes is not a trick of perception but a genuine effect of the geometry of spacetime. Time is inseparable from gravity, and where gravity deepens, time is dragged with it. Clocks near massive objects tick more slowly than clocks farther away. On Earth, this effect is tiny but measurable. Clocks on mountaintops run fractionally faster than those at sea level. In orbiting satellites, the difference is significant enough that the global positioning system must adjust for it. Near a black hole, the effect becomes extreme, so pronounced that it alters our very conception of past and future. This fact carries profound implications. It means that black holes are not merely destroyers of matter but sculptors of time. They reshape the flow of existence itself. A civilization living near a black hole could, in theory, experience time at a different pace than the rest of the universe. To them, centuries might pass as only decades outside. Or the opposite. A few years by their reckoning might mean eons unfolding in the wider cosmos. Black holes, in this way, are not only astronomical objects but also windows into the relativity of time. Reminders that the universe does not share a single clock but contains as many times as there are perspectives. There is something both humbling and exhilarating in this realization. We are creatures who measure life by steady rhythms, days marked by sunrise and sunset, years by the turning of seasons. To know that these rhythms are not universal but pliable, that time itself can be stretched and slowed, is to confront the strangeness of reality. Near a black hole, time becomes fluid, bending under gravity's hand like light curving through a lens. What we think of as unchanging is revealed to be fragile, dependent on where we stand in the great architecture of spacetime. This slowing of time also raises haunting questions about perspective and finality. To us, watching from afar, a person falling toward a black hole would never quite vanish. Their final approach would be stretched endlessly, their image lingering, fading slowly into darkness. Yet from within their own frame of reference, they would pass the horizon swiftly, crossing into a realm from which no message can return. Which perspective is true? Relativity teaches that both are, though they cannot be reconciled into a single story. The universe allows truths to diverge, each bound to its own path of time. The notion that black holes slow down time invites us to think of them not only as cosmic monsters but as profound teachers. They reveal that the universe is stranger than our instincts suggest, that reality is not rigid but supple, woven of a fabric that can bend under weight. Time, the most intimate dimension of our lives, is not universal but local, varying with gravity, altered by speed. We are not outside of this truth but inside it, our bodies and minds already participating in relativity, though only faintly compared to what unfolds near the abyss. To imagine standing on the edge of such a place, looking down into the invisible throat of a black hole, is to imagine staring into the distortion of time itself. The future and the present seem to blur. Eternity hovers just beyond reach, and what we thought immutable becomes fluid. That black holes can slow down time is not merely a scientific fact but a reminder that the universe exceeds our categories, that even the flow of moments is not safe from its mysteries. We live within a cosmos that bends the very essence of existence, a place where time is not a constant river but a shifting current, slowed, accelerated, and twisted by the gravity of stars collapsed into silence. Across the vastness of space, in every direction we look, there is a faint glow that has been shining since the dawn of time. It is not the light of stars or galaxies, nor the radiation from any single object. Instead, it is the lingering warmth of the universe's own birth, stretched and softened by the passage of nearly 14 billion years. This glow is known as the cosmic microwave background radiation, and it is the afterglow of the Big Bang itself, the oldest light we can see, a whisper from the universe's fiery beginning. To understand what it is, we must travel back to a time before there were stars, planets, or even atoms. About 13.8 billion years ago, the universe began as an unimaginably hot, dense state. In its earliest moments, temperatures were so extreme that matter as we know it could not exist. Instead, a seething soup of particles and radiation filled all of space. Photons, the particles of light, were constantly scattered by free electrons and protons in this dense plasma, unable to travel far without colliding. The universe was opaque, like the interior of a star, glowing fiercely but hiding its light within. As the universe expanded, it cooled. Over hundreds of thousands of years, the temperature gradually dropped from billions of degrees to just a few thousand. Then, about 380,000 years after the Big Bang, a pivotal transformation occurred. At around 3000 Kelvin, conditions became cool enough for protons and electrons to combine into neutral hydrogen atoms in a process known as recombination. With fewer free electrons to scatter them, photons were suddenly able to travel freely through space for the first time. In that moment, the universe became transparent, and the radiation that had once been trapped was released in a brilliant flash that filled all of space. That flash has been streaming across the cosmos ever since. Over the eons, as the universe continued to expand, the wavelengths of those ancient photons stretched, their energy diminishing. What began as a brilliant, white-hot glow in the visible and infrared range shifted into the microwave part of the spectrum. Today, this radiation is incredibly faint and cold, with a temperature of about 2.7 Kelvin, just above absolute zero. Yet it still fills the entire universe, bathing every corner of space in the same soft glow. No matter where we look, we see it, a relic of the time when the cosmos was less than 500,000 years old. The existence of this cosmic afterglow was predicted in the mid-20th century as a natural consequence of the Big Bang theory. Physicists realized that if the universe had indeed begun in a hot, dense state, there should be leftover radiation still detectable today, cooled and stretched by expansion but present everywhere. In 1965, by accident more than intention, two radio engineers, Arno Penzias and Robert Wilson, detected a persistent background noise with their antenna, noise that came from every direction and could not be explained by any known source. They had discovered the cosmic microwave background, providing one of the most compelling pieces of evidence for the Big Bang and transforming cosmology forever. Since that first detection, scientists have mapped the cosmic microwave background with ever-increasing precision. Early satellite missions like COBE, followed by WMAP and Planck, revealed that this ancient light is not perfectly uniform. It is astonishingly smooth, varying by only 1 part in 100,000, But those tiny fluctuations in temperature and density carry profound information. They are the imprints of the primordial ripples in matter and energy that, over billions of years, grew into galaxies, clusters, and the vast cosmic web that structures the universe today. In these faint patterns, scientists can read the story of the universe's infancy, its composition, its age, and even its ultimate fate. The cosmic microwave background is more than just evidence of the Big Bang. It is a kind of cosmic fossil, a snapshot of the universe when it was only a few 100,000 years old. Looking at it is like peering back in time to the universe's earliest chapter, long before the first stars were born. It tells us that the cosmos began hot and dense, that it has been expanding and cooling ever since, and that its large-scale structure grew from minute quantum fluctuations amplified over eons by gravity. It also acts as a cosmic reference point. The tiny variations in its temperature and polarization encode information about the universe's geometry, its rate of expansion, and the mysterious dark matter and dark energy that shape its evolution. Every photon of the cosmic microwave background has been traveling for nearly the entire history of the universe, untouched by anything except the steady stretching of space itself. When they reach the detectors on Earth or aboard space telescopes, they carry with them a message from the past. A message written when there were no galaxies, no stars, and no life. They remind us that the cosmos we see today, vast, complex, and full of structure, was once a uniform, glowing sea of particles and light. In a sense, the cosmic microwave background is the universe's memory. It holds within it the echoes of creation, preserved in the faintest possible form, waiting for us to decode. To listen to this ancient radiation is to hear the cosmos speak across almost 14 billion years, to touch the moment when time and space as we know them began. It is the afterglow of the Big Bang, still glowing softly in the darkness, a silent and enduring testimony to the universe's fiery birth. To imagine galaxies colliding is to confront a scale of violence and beauty far beyond human measure. A galaxy is a vast city of stars, hundreds of billions bound together by gravity, spinning in elegant spirals or clustered in glowing ellipses. They seem so serene when seen through a telescope, floating in the dark like luminous islands. Yet they are not fixed in space, not motionless ornaments pinned against the black. They move, drawn toward one another by gravity, tracing trajectories that span millions of years. And when their paths cross, they do not politely pass each other by. They merge, twist, and tear, their stars scattering into new patterns. Galaxies collide, and in those collisions, the universe reshapes itself. At first glance, the idea seems impossible. Stars within galaxies are separated by such enormous distances that even within a collision, the chance of two stars directly striking is vanishingly small. A star is small compared to the gulf that lies between it and its neighbors. If the sun were reduced to the size of a marble, the nearest star would be another marble thousands of kilometers away. In such a scenario, two galaxies passing through each other would be more like two clouds intermingling than two solid bodies crashing. And yet, the gravitational forces at work are immense. Though stars may rarely collide, the mutual gravity of two galaxies can pull them into distorted shapes, stretching their spiral arms into long streams, compressing gas clouds until they ignite in bursts of new star formation. Galaxies do not shatter like rocks. They transform, flowing into new forms, creating new generations of stars out of the turbulence. When we look into the night sky, we are not merely seeing galaxies as they are, but as they once were millions of years ago. Through telescopes, astronomers have captured snapshots of galaxies mid-collision. Two spirals entwined like dancers, tidal tails stretching out like luminous ribbons, cores beginning to sink into one another's gravity. These snapshots are not isolated curiosities but part of a larger pattern. Collisions are common in the history of the cosmos. Galaxies grow by merging. Our own Milky Way, vast and seemingly stable, has already absorbed smaller galaxies in its past, their stars now dispersed into its halo. It is not finished either. In a few billion years, it will collide with the Andromeda Galaxy, its nearest large neighbor. The night sky will be transformed as Andromeda looms larger and larger, until the two galaxies intertwine and eventually settle into a single, larger elliptical galaxy. The Earth may not survive long enough to see it, but the story is written in the trajectories of the stars. The collision of galaxies is not only a spectacle but a crucial engine of cosmic evolution. Gas clouds, otherwise floating serenely, are shocked and compressed by the gravitational tides of merging galaxies, triggering starbursts, rapid waves of star formation that light up the universe. Entire regions can flare into being, birthing clusters of stars that would never have formed without the upheaval. At the same time, the central black holes in galaxies, usually dormant, can be jolted into ferocious activity, feeding on infalling gas and blazing as quasars. In this way, collisions sculpt not only the shapes of galaxies but the lives of stars, the birth of planets, the very conditions under which life might one day emerge. There is something paradoxical about these events. From our perspective, a collision suggests suddenness and destruction, but a galactic collision unfolds across spans of time so immense that no human word quite fits. It takes hundreds of millions of years for galaxies to pass through one another, and billions before they settle into their final form. To any creature within such a galaxy, the collision would not appear as an event at all, but as a slow transformation, as if the stars themselves were drifting into new constellations over eons. The violence is stretched into grandeur, destruction mingled with creation. The knowledge that galaxies collide shifts our understanding of the cosmos. It shows that the universe is not static, not a collection of frozen structures hanging in empty space. It is dynamic, restless, alive with motion. The beauty we admire in a spiral galaxy is not a permanent form but a passing phase, one moment in a long story of change. Galaxies are born, grow, collide, and merge, just as living things do, though on scales of time that dwarf our own. The universe is not only immense but in motion, reshaping itself through encounters written into its very fabric. And yet, there is also wonder in knowing that these colossal collisions are not the end of things but the beginning of new ones. The stars of colliding galaxies rarely perish in the meeting. Instead, they find themselves in new orbits, part of a new whole. Out of turbulence comes new structure. Out of compression comes new light. The collision of galaxies is the universe's way of renewing itself, of building larger forms out of smaller ones, of weaving complexity out of chaos. To think of galaxies colliding is to realize that the night sky we know is temporary, that the calm beauty of the Milky Way will someday give way to a different vista. It is to realize that destruction and creation are not opposites in the cosmos but partners in the same dance. The stars above us bear witness to a history of collisions already past, and their descendants will shine on in galaxies not yet born. The universe is not still. It is a grand choreography, galaxies drifting and colliding, reshaping themselves endlessly in the long, slow rhythm of time. A neutron star is one of the strangest and most extreme objects in the universe, a place where matter is crushed beyond the limits of our ordinary imagination. To say that it is dense is an understatement so severe that words falter. Density in the human world is a simple concept. We say iron is dense compared to wood, lead denser still. Even gold, heavy in the hand, can be grasped by our senses. But a neutron star is so dense that such comparisons break down. A single teaspoon of its matter would outweigh mountains. Some calculations put that spoonful at around 1 billion tons, more than all the cars, ships, and buildings on Earth combined. This is not density as we know it. This is density pushed to the edge of physics, where atoms themselves collapse and ordinary matter becomes something altogether new. A neutron star is the remnant of a massive star's death. When a star much larger than our Sun exhausts its fuel, its core can no longer resist gravity's pull. The outer layers explode in a supernova, scattering elements across space, but the core collapses inward. Under pressure so immense that electrons are squeezed into protons, forming neutrons, the matter of the star is compacted into a sphere only about 20 kilometers wide. Imagine a star larger than the Sun crushed down to the size of a city. The result is an object of such ferocious density that it defies ordinary analogies. It is not a planet, not a star in the familiar sense, but something between, a stellar corpse that still glows with heat and spins with unearthly speed. What makes a neutron star so dense is the nature of neutrons themselves. In ordinary matter, atoms are mostly empty space. Tiny nuclei surrounded by vast clouds of electrons. The distances between these particles are enormous compared to their size, which is why a solid object is still mostly emptiness. But in a neutron star, the emptiness is crushed away. Electrons and protons combine, leaving neutrons packed shoulder to shoulder in a dense nuclear lattice. The entire star becomes like one giant atomic nucleus, a mass of neutrons pressed together so tightly that no space remains. It is matter stripped of its familiar structure, reduced to its most compressed form short of becoming a black hole. The physical consequences of such density are astonishing. Gravity at the surface of a neutron star is immense, hundreds of billions of times stronger than Earth's. A human standing there, if it were possible to stand at all, would be flattened instantly into a smear of subatomic particles. Light itself struggles to escape. Photons leaving the surface are bent and redshifted by the gravity, making the star appear dimmer and redder than it otherwise would. The crust of a neutron star, though only a few centimeters thick, is so rigid that it could withstand pressures that would pulverize steel like dust. Even mountains on its surface, if they exist at all, would be measured not in kilometers but in centimeters, so strong is the pull to smooth everything flat. Yet neutron stars are not inert. Many rotate with extraordinary speed, completing hundreds of revolutions each second. As they spin, their magnetic fields whip around, emitting beams of radiation that sweep across space. When these beams cross Earth, we detect them as pulses, pulsars, cosmic lighthouses ticking with the precision of a clock. These pulses can be so regular that they rival atomic clocks in their steadiness, offering astronomers a tool to measure cosmic phenomena with exquisite accuracy. All of this order and regularity arises from the raw density of the neutron star, from the way matter has been crushed to its absolute limits. To think of density on such a scale is to encounter the limits of human comprehension. We can imagine a brick heavy in the hand. We can imagine steel heavy in the arm. But to imagine a star's worth of mass compressed into something the size of a city is to leave the realm of experience. We have no sensory reference for this. It is a fact we can state, calculate, even test, but not truly imagine in its fullness. Our metaphors collapse and we are left with awe. The density of a neutron star is a reminder that the universe contains realities that stretch far beyond the scale of our lives, realities that cannot be reduced to familiar images. This density also carries a strange beauty. It is the density that makes neutron stars the forges of mystery, the laboratories of extremes. When two neutron stars collide, their densities combine in a cataclysm so fierce that space itself ripples with gravitational waves. These collisions scatter heavy elements, gold, platinum, uranium, into space, seeding future planets and stars. The jewelry on a hand, the circuitry in a computer, the fuel in a reactor may all have been born in the moment when two impossibly dense stars merged and tore themselves apart. What seems alien and remote is, in truth, woven into our lives. To say neutron stars are insanely dense is thus more than a fact of physics. It is a way of acknowledging how strange and varied the universe is, how it can take matter we think we know and push it into states beyond comprehension. They are reminders that nature does not end at the limits of human experience but continues, inexhaustibly, into realms of extremity where imagination falters. A neutron star is not only an object in the sky but a testament to the possibility that reality is richer, denser, and more astonishing than anything we can hold in our hands. In the darkness of the cosmos, scattered among the billions of galaxies, there are objects so dazzling that they outshine everything around them. These cosmic beacons, called quasars, blaze with a brilliance that defies intuition. A single quasar can emit more light than an entire galaxy of hundreds of billions of stars. Seen from billions of light-years away, they pierce the fabric of space like cosmic lighthouses, their light having traveled for eons to reach us. They are among the most luminous and energetic phenomena in the universe, born from the most extreme environments known, supermassive black holes devouring matter at the hearts of distant galaxies. Quasars, short for quasi-stellar radio sources, were first discovered in the 1950s and 1960s as mysterious points of light in radio surveys of the sky. At first, astronomers thought they were stars because they appeared as tiny, star-like dots even through powerful telescopes. But their spectra told a different story. The light they emitted was highly redshifted, meaning it came from objects billions of light-years away. For them to be visible from such distances, they had to be unimaginably luminous, far brighter than any star. It became clear that quasars were not stars at all but something entirely new. The blazing hearts of distant galaxies, powered by processes far more energetic than stellar fusion. At the center of almost every large galaxy lies a supermassive black hole, millions or billions of times the mass of the Sun. On their own, black holes emit no light, but when gas and dust spiral into them, they unleash astonishing amounts of energy. As matter falls inward, it forms a swirling accretion disk that heats up through friction to millions of degrees, radiating across the electromagnetic spectrum, from radio waves to visible light to X-rays. Jets of particles, accelerated to near-light speed by magnetic fields, can shoot out from the poles, stretching across intergalactic space. The result is a quasar, a compact region of furious energy generation capable of outshining an entire galaxy. The sheer scale of their luminosity is almost beyond comprehension. A typical quasar can be 1,000 times brighter than the Milky Way, even though its light comes from a region smaller than our solar system. Some of the most powerful quasars emit as much energy as 1 trillion suns. Yet this brilliance is not eternal. Quasars are fueled by the steady flow of material into their central black holes, and when that supply runs out, they fade. Most galaxies, including our own, likely went through quasar phases in their youth, when gas was more plentiful and galaxy collisions funneled vast amounts of material toward their cores. Because they are so bright, quasars are visible across enormous cosmic distances. Some of the most distant quasars we have observed formed less than 1 billion years after the Big Bang, their light traveling more than 13 billion years to reach us. They are, in a sense, time capsules, revealing what the universe was like when it was still young and galaxies were just beginning to take shape. Studying them gives astronomers a window into the early cosmos and the growth of supermassive black holes. Their intense radiation also illuminates the intergalactic medium, allowing scientists to trace the structure and composition of the universe across vast scales. Quasars also serve as signposts of cosmic evolution. They seem to flourish during an era when galaxies were actively merging and growing, a period of cosmic adolescence roughly 10 billion years ago. Collisions between galaxies funneled gas into their centers, triggering the feeding frenzies that powered quasars. As galaxies matured and their gas supplies dwindled, quasars became rarer. Today, active quasars are relatively uncommon, though the dormant supermassive black holes that once powered them remain in the centers of most large galaxies, including our Milky Way. Their power is not just a spectacle. It can profoundly shape their host galaxies. The intense radiation and powerful winds driven by quasars can blow away gas and dust, quenching star formation and influencing how galaxies evolve. This process, known as feedback, may help explain why galaxies and their central black holes grow in tandem, their masses tightly correlated. Quasars, then, are not just byproducts of galactic evolution. They are key players in shaping the galaxies we see today. Despite decades of study, many mysteries about quasars remain. How did supermassive black holes grow so quickly in the early universe? What triggers the transition from a quiet galaxy center to a raging quasar? How exactly do the colossal jets they produce accelerate particles across millions of light-years? These questions drive some of the most active research in astrophysics today. With new telescopes and instruments, scientists are peering deeper into space and time, discovering quasars from earlier and earlier epochs and unraveling their secrets. It is humbling to realize that something so luminous, so powerful, and so distant could be powered by something as paradoxical as a black hole, a region from which not even light can escape. Yet this paradox is central to the story of quasars. They exist at the intersection of gravity and energy, darkness and brilliance. The same force that traps light within a black hole's event horizon also fuels the most radiant objects in the cosmos. Quasars remind us of the universe's extremes. They show us that cosmic power is not limited by the size of stars or galaxies, but can be concentrated in a space no larger than our solar system. They illuminate the early history of the universe, guide us in mapping the cosmos, and reveal the turbulent relationship between galaxies and their central black holes. Even across billions of light-years, their light reaches us, carrying stories from a universe long past. And in that light, brighter than all the stars of a galaxy combined, we glimpse both the fury and the grandeur of the cosmos. For decades, astronomers believed that dark matter was an inseparable companion to galaxies, an invisible framework that shaped their formation and held them together. According to this view, every galaxy, from the smallest dwarf to the largest spiral, owes its existence to the gravitational pull of dark matter. Without it, the gas and stars that make up a galaxy would not have enough gravity to remain bound, and the swirling disks of light we see in the night sky would simply drift apart. Yet in recent years, a surprising discovery has challenged this long-held assumption. Some galaxies appear to contain little or no dark matter at all. This revelation has forced scientists to rethink what they thought they knew about how galaxies form and evolve. Dark matter itself remains one of the great mysteries of modern science. It does not emit, absorb, or reflect light, making it invisible to telescopes. Yet its presence is revealed through its gravitational influence. Galaxies rotate faster than they should if only the visible matter were present, and galaxy clusters contain far more mass than can be accounted for by stars and gas alone. These and many other observations point to dark matter making up about 85% of all matter in the universe. It has long been considered the cosmic scaffolding on which galaxies are built, shaping their structure from the earliest moments after the Big Bang. That is why the discovery of galaxies apparently lacking dark matter was so startling. In 2018, astronomers studying a faint, diffuse galaxy known as NGC 1052 DF2, about 65 million light-years away, found that the stars within it were moving far more slowly than expected. This meant that the galaxy's total mass was roughly equal to the mass of its stars alone, There was little room for the vast reservoir of dark matter thought to exist in all galaxies. Soon after, a second galaxy, NGC 1052, DF4, showed similar behavior. These were not tiny dwarf galaxies but relatively large, extended systems with properties unlike anything astronomers had seen before. The discovery was met with both excitement and skepticism. Some wondered whether the measurements were mistaken or whether the galaxies were being misinterpreted. But further studies with more precise instruments confirmed the findings. These galaxies truly seemed to lack dark matter. This raised a profound question: how could galaxies like these exist at all? If dark matter is essential for galaxy formation, as current models suggest, then galaxies without it should be impossible. One explanation is that these galaxies did form with dark matter but lost it later through gravitational interactions. Both DF2 and DF4 lie near a massive elliptical galaxy, NGC 1052, whose strong gravity could have stripped away their dark matter halos during close encounters. Such a process, though rare, might leave behind galaxies made almost entirely of ordinary matter. Another possibility is that these galaxies formed in an unusual way, perhaps as the result of galactic collisions that flung out gas and stars but not dark matter, leading to their unusual composition. These discoveries do more than challenge assumptions. They provide valuable tests of our theories about dark matter itself. If galaxies without dark matter can exist, it suggests that dark matter behaves as an independent component of the universe, capable of being separated from ordinary matter under certain conditions. This reinforces the idea that dark matter is not simply a modification of gravity, as some alternative theories propose, but a distinct form of matter with its own properties and dynamics. Observing how galaxies like DF2 and DF4 came to be could help reveal the nature of this mysterious substance and how it interacts with the visible universe. The existence of such galaxies also teaches us that the universe is more diverse and complex than our models sometimes assume. For decades, astronomers built their understanding of galaxy formation on the idea that dark matter halos are essential to the process. The presence of galaxies that seem to defy this rule suggests that there are other pathways to galactic evolution, rare and unusual perhaps, but real. They remind us that the cosmos often resists our efforts to categorize it neatly, and that exceptions can reveal more about the rules than the rules themselves. Yet mysteries remain. Are DF2 and DF4 rare exceptions? Or are there many more dark matter deficient galaxies waiting to be found? How exactly did they lose or fail to acquire their dark matter? Could some galaxies exist at the other extreme, containing only dark matter and almost no stars? Astronomers are now searching the skies for more examples, hoping that a larger sample will offer clearer answers. As new telescopes peer deeper into the universe and collect more precise data, the picture may become sharper. The discovery of galaxies without dark matter is a reminder of how science progresses. Just when we think we have the universe figured out, it surprises us with something unexpected. These strange galaxies do not overturn everything we know about dark matter, but they complicate the story and deepen the mystery. They hint that dark matter's role in galaxy formation may be more flexible and nuanced than we imagined, and that the universe's creativity extends beyond the boundaries of our current theories. In the end, these ghostly galaxies, faint and diffuse against the backdrop of space, challenge us to look deeper into the cosmos and question our assumptions. They show us that even the most fundamental ideas in astrophysics are not beyond revision, and that the universe still holds secrets capable of reshaping how we see it. Whether they are cosmic anomalies or pieces of a larger pattern we have yet to understand, galaxies without dark matter stand as a testament to the complexity of creation, and a reminder that the universe is always more mysterious than we think. In the deepest reaches of the cosmos, where gravity reigns supreme and light itself can be trapped, lie the most mysterious and powerful objects known: black holes. Born from the collapse of massive stars or from the growth of ancient cosmic seeds, Black holes come in many sizes, from a few times the mass of our Sun to millions or even billions of solar masses. Yet even among these cosmic giants, one stands out as a true colossus. A black hole so vast and heavy that it defies imagination. The largest known black hole discovered so far is estimated to have a mass more than 66 billion times that of the Sun, a gravitational monster lurking at the center of a distant galaxy and stretching the limits of what we thought possible in the universe. This behemoth resides in the core of the galaxy cluster Abell 1201, about 2.7 billion light-years from Earth. Astronomers detected its presence not by directly observing the black hole, an impossible task since no light can escape its pull, but by studying how its immense gravity bends and magnifies the light of more distant galaxies behind it, a phenomenon known as gravitational lensing. The scale of the lensing effect revealed that the galaxy's central mass was far larger than expected. When the calculations were complete, the results stunned scientists. The black hole anchoring Abell 1201 central galaxy must have a mass exceeding 66 billion suns. To grasp what that means, consider that the black hole at the heart of our own Milky Way, Sagittarius A*, weighs about 4 million solar masses, already vast beyond comprehension. The black hole in the galaxy M87, one of the largest previously measured, has a mass of around 6.5 billion suns and was the first to be directly imaged. The black hole in Home 15A, another record holder, weighs about 40 billion solar masses. Yet all of these pale beside the Leviathan in Abell 1201, which dwarfs them several times over. Its event horizon, the point of no return, would stretch across hundreds of billions of kilometers, larger than the orbit of Pluto many times over. How such a gigantic black hole forms is still a subject of intense research. The universe began with black holes much smaller than this, likely just tens or hundreds of solar masses, formed from the deaths of the first stars. Over billions of years, they grew by devouring gas, dust, stars, and even other black holes. Some black holes grew rapidly in the crowded hearts of galaxies, where streams of matter funneled inward to feed them. Others may have merged during galaxy collisions, each merger producing an even larger remnant. But for a black hole to reach tens of billions of solar masses, ordinary feeding and merging may not be enough. It may require a special set of conditions, perhaps the collapse of a gigantic primordial gas cloud in the early universe or an environment that continually supplied vast amounts of material for eons. These extreme black holes are sometimes called ultramassive black holes, a class beyond even the supermassive black holes found in most galaxies. They sit at the centers of galaxy clusters, where gravity pulls entire galaxies together and where the density of matter provides abundant fuel. Their growth is tied closely to the growth of the galaxies and clusters around them. As the black hole grows, it shapes its surroundings. Its gravitational pull influences the motion of stars and gas across thousands of light-years, and its powerful jets and radiation can heat and blow away matter, regulating star formation in the host galaxy. The existence of a 66 billion solar mass black hole forces astronomers to rethink the upper limits of black hole growth. Some theories predicted that black holes could not exceed around 50 billion solar masses because radiation pressure from infalling matter would eventually choke off further feeding. Yet nature has clearly found a way to surpass that barrier. This hints that our understanding of black hole physics, especially in the most extreme environments, may still be incomplete. It also suggests that even larger black holes may exist, hidden in the hearts of other massive galaxies still waiting to be discovered. What makes black holes like this even more fascinating is their paradoxical nature. Despite their unimaginable mass, they are incredibly compact. A black hole tens of billions of times heavier than the Sun could still fit inside the orbit of Neptune. Their gravitational pull is so strong that nothing, not even light, can escape once it crosses the event horizon. Yet beyond that invisible boundary, Space and time themselves are warped into forms we can scarcely imagine. At the core, where the laws of physics as we know them break down, lies a singularity, a point of infinite density where matter is crushed out of existence and our understanding of reality fails. For astronomers, discovering such colossal black holes is more than just a record-breaking achievement. It offers a glimpse into the universe's deepest past and most violent processes. The light bent and magnified by the black hole in Able 1201 tells stories billions of years old, revealing how matter and energy behaved when galaxies were young. It helps scientists test the limits of general relativity, Einstein's theory of gravity, under the most extreme conditions known. And it sheds light on the role black holes play in shaping the large-scale structure of the cosmos. Standing on Earth, orbiting an ordinary star in an ordinary galaxy, it is difficult to truly comprehend the scale of such a cosmic monster. Yet out there, in the silent heart of a distant cluster, a black hole more than 66 billion times the mass of the Sun waits, invisible but all-powerful, shaping the galaxies around it and bending the very fabric of space. It is a reminder that the universe is still capable of astonishing us, that its extremes are far greater than we once believed. And as our telescopes grow sharper and our tools more precise, we may find that even this cosmic giant is not the ultimate limit, that somewhere in the depths of the universe, still greater black holes are hiding, waiting for us to discover them. When we speak of the universe, we often imagine it as a great expanse of space with some hidden point of origin, a central place from which all things spread outward. Our minds, trained by daily experience, long to anchor things in a familiar framework. Every circle has a midpoint, every explosion a starting point, every journey a departure. It seems natural to assume the universe, being the largest thing we can conceive, should also be organized around some center, a privileged location that carries the weight of ultimate importance. Yet modern cosmology has shown us that this is not the case. The universe, in its vastness, is without a center. Every point is just as much a part of the whole as any other. The absence of a cosmic middle unsettles some, but it also opens the imagination to a more radical form of belonging. We are not located at the edge or at the hub, but simply within, and that is enough. The reason for this lies in the way the universe expands. We know, through observations of galaxies drifting away from one another, that space itself stretches. This expansion does not happen as it might in the case of a cloud of dust bursting from a point into empty air, with particles radiating out from the explosion's origin. If it were so, then one could mark the location of the blast and declare it the center. Instead, the expansion is woven into the very fabric of spacetime. Galaxies recede from one another not because they are flying through some surrounding void, but because the distances between them are being stretched by the growth of space itself. Every point of space expands relative to every other point. From any vantage, one will see galaxies retreating in all directions, as though one occupies the center. And yet no place holds that privilege. The illusion of centrality is granted everywhere equally. A familiar analogy is the surface of a balloon being inflated. Imagine specks of paint dotted on its skin. As the balloon swells, the specks move apart, though none is truly at the center of the surface. The center exists only if you step outside the surface and regard the balloon from a higher dimensional perspective. Within the two-dimensional world of the surface itself, there is no special spot from which expansion radiates. What holds for that thin surface holds for the universe in 3 dimensions. If it has a center, it lies outside our universe in some hypothetical vantage beyond the cosmos. But such an outside is not available to us, and perhaps does not exist at all. The universe is everything there is. Its center cannot be placed because there is nothing external to contain it. This understanding reframes the place of humanity in the cosmos. For centuries, people assumed that Earth occupied the middle of creation. It was natural to think so, because our senses place us here, at the axis of our own horizons. When science dismantled that geocentric picture, replacing it with the heliocentric model of the solar system, the loss of centrality seemed like a demotion. Later, when the Milky Way was shown to be only one galaxy among billions, the sense of smallness deepened. And now, with the revelation that the universe itself has no center, the final vestige of privileged position disappears. It may appear humbling, even disorienting, to inhabit a reality without a cosmic focus. But it also frees us from a hierarchy of places. If there is no center, there is no periphery either. Every location is equally central, equally peripheral. Our coordinates are arbitrary, and yet they are enough to give us existence. In this view, Earth is not diminished. It is as central as any other point could be, which is to say, it is uniquely itself. There is a strange beauty in this symmetry. A universe without a center suggests a universe without favoritism. It resists the urge to crown a single position as the anchor of reality. Instead, it teaches us that importance is not spatial but relational. What matters is not where we are located in some imagined cosmic diagram, but how we live within the unfolding whole. Just as the stars do not require a throne at the hub of the cosmos to burn brightly, so too humanity does not need a central pedestal to find meaning. The absence of a center invites us to release the desire for cosmic hierarchy and instead to embrace the evenness of existence. In truth, the notion of a center is something the human mind imposes, trained as it is by geometry and by the small spaces of daily life. Rooms have centers. Tables do. Cities have squares. Nations have capitals. Our bodies themselves are oriented by a center of gravity, a middle around which movement balances. To imagine something as boundless as the universe without such an anchor requires us to stretch the imagination beyond the habits of scale. We must accept that the rules of our kitchen and courtyard do not apply to the grand fabric of spacetime. What is natural at human measure may dissolve at cosmic measure. The universe teaches us humility in this way, by showing that our intuitions, useful as they are for survival, falter when applied to the whole of existence. And yet, in the very act of stretching beyond these intuitions, we glimpse a new kind of wonder. The universe has no center because it is not an object in space, floating within some larger emptiness. It is the totality of space and time themselves, unfolding without an external frame. To ask for its center is like asking for the north of the North Pole. The question misfires. The answer is not that we are at the edge or the middle, but that every point contains within it the same dignity of being part of everything. To live here, on this small planet orbiting a middling star, is to live in the very heart of the universe, for there is no place that is not at its heart. In the end, the absence of a center does not diminish us. It enfolds us in the profound equality of all things. For most of human history, the universe seemed eternal and unchanging, a vast stage on which the drama of stars and planets unfolded forever. Yet modern science tells a different story, one far more dynamic and unsettling. The universe, it turns out, is not a timeless backdrop but a living, evolving entity with a beginning, a history, and possibly an end. Born in a fiery burst nearly 13.8 billion years ago, it has been expanding, cooling, and changing ever since. And just as it had a beginning, it may one day have an ending. The cosmos might not last forever. It could be finite-lived, destined to fade, collapse, or transform beyond recognition in the distant future. Our understanding of the universe's potential fate begins with the discovery of its origin. The Big Bang Theory, now firmly supported by observation, tells us that the universe began as an incredibly hot, dense state and has been expanding ever since. Galaxies drift apart, the fabric of space itself stretches, and the cosmos grows larger and colder over time. For decades, scientists debated whether this expansion would continue forever or eventually slow and reverse. The answer depends on the contents of the universe, its matter, energy, and the mysterious force known as dark energy that drives its accelerated expansion. If the universe is finite-lived, its story will end in one of several possible ways. One scenario is the Big Crunch, in which the expansion eventually halts and reverses. Gravity, the great sculptor of cosmic structure, could one day overcome the outward push, pulling galaxies back together. Over billions of years, the universe would contract, growing hotter and denser until all matter collapsed into a final, catastrophic singularity. This would mirror the Big Bang in reverse, a cosmic implosion that ends time as we know it. While once considered likely, this fate now seems less probable because observations show that the universe's expansion is not slowing down but accelerating. That acceleration leads to another, perhaps more haunting possibility: the Big Freeze. In this scenario, the universe keeps expanding forever, but as it does, galaxies drift farther apart and stars exhaust their fuel. Over trillions of years, star formation will cease, existing stars will burn out, and the cosmos will grow darker and colder. Black holes, the last luminous objects, will slowly evaporate through Hawking radiation, leaving behind only a thin mist of particles in an almost featureless void. This heat death marks not a sudden end but a slow, inevitable fading, as the universe approaches absolute zero and entropy reaches its maximum. Time itself may lose meaning when nothing changes anymore. There is also the more dramatic Big Rip, a fate born from the mysterious nature of dark energy. If this repulsive force grows stronger over time, it could tear the universe apart. Galaxies would be pulled away from each other, then stars from galaxies, then planets from stars. Eventually, even atoms and subatomic particles could be ripped apart as space-time itself stretches beyond all bounds. The Big Rip would bring the universe to an abrupt and violent end, shredding everything in a final moment of infinite expansion. Whether this occurs depends on the precise properties of dark energy, something we still do not fully understand. Even stranger possibilities exist. Some cosmologists speculate that the universe might one day undergo a vacuum decay, triggered by a quantum event. If our universe's vacuum state is not the most stable possible, a more stable state could emerge, spreading through space at nearly the speed of light and annihilating everything in its path. This would rewrite the laws of physics in an instant and erase the cosmos as we know it. Such a fate would come without warning, and though highly speculative, it reminds us that the universe's stability is not guaranteed. The idea that the universe could end is more than a scientific curiosity. It reshapes how we think about existence. A finite-lived cosmos means that even the grandest structures, from galaxies to clusters to the cosmic web itself, are temporary. It means that time has direction, that the universe is a story with a beginning, middle, and end. The stars we see tonight are part of a fleeting era, one that will pass just as surely as the ages before it. Even the laws of nature might not be eternal, but chapters in a larger cosmic narrative. And yet, within this finite span, the universe has created extraordinary complexity. It forged galaxies from hydrogen, planets from dust, and life from stardust. It gave rise to minds capable of contemplating its origins and fate. The fact that it may one day end does not diminish its grandeur. If anything, it makes its story more poignant. A universe without an ending might seem timeless and unchanging, but one with a finite life is a universe in motion, alive with transformation and possibility. Though we cannot yet know which fate awaits us, the question drives some of the most profound research in cosmology. Scientists measure the universe's expansion, probe the nature of dark energy, and study the cosmic microwave background to learn how the cosmos has evolved and where it is heading. Each new discovery brings us closer to understanding the universe's destiny and our own place within it. The universe's finiteness reminds us that impermanence is woven into the fabric of reality itself. Just as stars are born and die, so too might the cosmos that contains them. Whether it ends in fire or in cold, with a bang or a whimper, its story is still unfolding. And for now, we live within one brief chapter of that story, looking out into the vastness and wondering how it will end. When we first looked up at the stars, we assumed they were the main characters of the universe. Stars shine, they warm planets, they fill the night with light. Planets, by contrast, are quiet, hidden companions, visible only in the rare cases where they reflect their parent stars' glow strongly enough to be seen from afar. For most of human history, Earth seemed exceptional, accompanied by its sun and its moon, with only a handful of other worlds visible to the eye. It was natural to think planets were rare, perhaps peculiar to our own solar system. But modern astronomy has upended that assumption. Evidence now suggests that planets may actually outnumber stars in our galaxy, that for every star we see blazing across the night, there may be one, two, or even many more planets orbiting invisibly around it. The stars, dazzling as they are, may be only the scaffolding of a much richer population of worlds. The discovery began modestly. In the 1990s, the first planets beyond our solar system, exoplanets, were detected. At first, they seemed odd giants orbiting perilously close to their stars, configurations nothing like our own solar system. Many doubted whether planets were truly common. But as technology improved, thousands more were found. Through careful methods like observing the tiny dimming of a star's light as a planet crosses in front of it, or measuring the subtle wobble in a star's motion caused by the pull of orbiting companions. From these discoveries, astronomers began to notice a pattern. Planets are not rare at all. In fact, they are everywhere. Almost every star seems to host at least one, and many host entire systems, some with dozens of worlds. If this is true, the implications are staggering. The Milky Way contains around 400 billion stars. If even most of them host planets, then there could be trillions of planets in our galaxy alone. And the reality may be more extreme still, because some planets are not bound to stars at all. They wander through the galaxy as rogue planets, ejected from their systems by gravitational upheavals, drifting through the darkness without a sun. These hidden wanderers could be as numerous as the tethered planets. If so, then the number of planets in our galaxy may exceed the number of stars by far. The image of the galaxy changes in this light. Not a great city of stars surrounded by a scattering of planets, but a vast archipelago of worlds, stars serving only as lamps that illuminate some of them while countless others drift unseen. The idea that planets are more abundant than stars also changes how we think about the universe's generosity. For centuries, we thought of Earth as unique, perhaps singular. Now we see that planets are not the exception but the rule. Every point of light in the sky is not only a star but a potential solar system, a stage upon which the drama of geology, chemistry, and maybe even life could unfold. The galaxy becomes not a desert dotted with rare oases, but a forest thick with possibilities, with worlds of every shape and size scattered like leaves. Some may be barren, scorched, or frozen, but some may be temperate, water-rich, and capable of harboring life. The fact that planets may outnumber stars suggests that the universe is far more generous with potential than we ever dared to dream. This abundance also reshapes our sense of proportion. Stars dominate the night sky because they emit light, but they may actually be outnumbered by their quieter companions. It is like discovering that the visible world is only a thin layer, while the invisible is far greater. We stand on a planet orbiting a star, and for most of human history we thought this arrangement was unusual, but it may be the most common arrangement of all. The ordinary is, in fact, the extraordinary. The night sky becomes not a collection of lonely lights but a map of unseen worlds. Yet the possibility of more planets than stars is not only a matter of numbers. It is a matter of imagination. Each planet, whether orbiting close to its star or wandering free, is a place. A landscape, a surface, perhaps an atmosphere, weather, and features we cannot guess. To know there may be trillions of such places in our galaxy is to open the mind to an almost unbearable vastness. Each planet is not just a statistic but a potential story, a potential world with its own history written in stone and air. The abundance of planets means the abundance of difference, of variation, of possibility. Some may be small and rocky like Earth, others immense and gaseous like Jupiter, others ocean worlds, ice worlds, lava worlds. Each star becomes not merely a point of light but a seed around which a family of worlds might form. There is a humility in recognizing that Earth, for all its richness, is only one among trillions. But there is also wonder. The galaxy is not empty but crowded, not sparse but teeming with unseen worlds. When we look up at the stars, we are not merely seeing lights in the darkness. We are glimpsing the faint markers of a far greater reality. Around each star, hidden from sight, may circle worlds as real as ours, each with its own skies, its own landscapes, its own silences. Some may forever remain unknown, unreachable, unseen. Yet their existence reminds us that the cosmos is not poor but abundant, not stingy but overflowing. To think there may be more planets than stars is to realize that we live in a galaxy of worlds. Our own Earth is one among countless others, unique in its particulars but not alone in its kind. The stars are only the lanterns. The true richness of the galaxy lies in the worlds they illuminate, and in the still greater number of worlds that remain in the dark. When we gaze into the night sky, we see a universe that feels vast beyond comprehension. Billions of galaxies, each with billions of stars, stretching across space and time. It seems infinite, yet it may be only a single bubble in a much larger cosmic sea. Scientists and philosophers have long wondered if our universe is unique, or if it is just one of many. This idea, known as the multiverse, suggests that reality might extend far beyond the limits of what we can observe, encompassing countless other universes, each with its own laws of nature, histories, and perhaps even versions of ourselves. Though still theoretical, the multiverse is one of the most intriguing and profound ideas in modern science. The concept arises naturally from our best theories about the origins and nature of the cosmos. According to the Big Bang model, our universe began about 13.8 billion years ago as a hot, dense point that expanded and cooled over time. But some versions of cosmic inflation, a theory describing a rapid expansion that occurred a fraction of a second after the Big Bang, imply that this explosive beginning may not have been unique. In these models, space itself undergoes inflation eternally in some regions, spawning bubble universes, where inflation ends and normal cosmic evolution begins. Our observable universe could be one such bubble, floating in an infinite froth of other universes born from the same primordial process. If eternal inflation is correct, then the multiverse is not merely a philosophical speculation but a natural consequence of cosmic physics. Each bubble universe could have its own distinct properties. Some might be governed by the same fundamental constants and forces we know, while others might differ radically. In one universe, gravity might be stronger. In another, atoms might not form at all. Some might contain galaxies, stars, and life, while others might remain dark and sterile. The landscape of possibilities is staggering, perhaps infinite, and within that landscape, our universe is just one particular realization among countless others. The multiverse also appears in other branches of physics, each offering a different perspective on how multiple universes could exist. In quantum mechanics, for example, the many worlds interpretation suggests that every quantum event branches into different outcomes, each realized in its own separate universe. According to this view, every time a choice is made or a particle's position is measured, reality splits, creating parallel worlds that evolve independently. In one, a coin lands heads. In another, it lands tails. In one, a star forms a solar system much like ours. In another, it collapses into darkness. These universes are not distant in space but in possibility, unfolding alongside ours in an ever-branching tree of quantum events. String theory, an ambitious attempt to unify all fundamental forces, introduces yet another version of the multiverse. It predicts a vast landscape of possible solutions, each corresponding to a universe with its own set of physical laws. The sheer number of these solutions, perhaps 10 to the power of 500 or more, is so enormous that our universe may be just one point in a virtually infinite space of possibilities. In this view, the multiverse is not an optional add-on but a natural outcome of the mathematics underlying reality itself. The idea of a multiverse raises profound philosophical and scientific questions. If other universes exist beyond our observational reach, can we ever know them? By definition, anything beyond our cosmic horizon lies outside the realm of direct observation, making the multiverse difficult, perhaps impossible, to confirm in the traditional sense. Critics argue that without testable predictions, the multiverse is more metaphysics than science. Yet its defenders counter that it emerges naturally from theories that have already proven successful in explaining what we do see. If those theories are correct, then the multiverse may be a logical consequence, even if we cannot touch it directly. There are, however, subtle ways the multiverse might leave traces in our own universe. Some physicists have proposed that collisions between bubble universes in the early cosmos could leave faint imprints in the cosmic microwave background, the ancient afterglow of the Big Bang. Others search for statistical clues, such as the fine-tuning of physical constants, that might hint at a larger ensemble of universes. Our universe appears remarkably suited for life, with physical laws balanced in ways that allow stars, planets, and biology to exist. In a multiverse, this fine-tuning might not be surprising. If countless universes exist with different laws, we find ourselves in one that supports life simply because we could not exist in the others. Beyond science, the multiverse reshapes how we think about existence itself. It suggests that reality may be far vaster and stranger than we ever imagined, that the cosmos we inhabit is not the totality of all that is but just a single page in an infinite cosmic library. It blurs the line between necessity and chance, raising the possibility that our universe's properties are not uniquely determined but merely one set among countless variations. It even challenges our sense of uniqueness, hinting that other versions of ourselves might exist in worlds with different histories and choices. Whether the multiverse is real remains one of the great open questions of modern science. For now, it exists as a bold and tantalizing idea, a bridge between the known universe and the boundless unknown beyond. It invites us to think bigger than galaxies and cosmic horizons, to imagine a reality without edges or limits, where the cosmos is not a single universe but a vast and eternal ensemble. Perhaps, somewhere beyond the reach of our telescopes, countless other universes are unfolding their own stories, born in the same cosmic fire that gave rise to ours. And perhaps, as our understanding deepens, we will find that what we call the universe is just the smallest piece of a much grander whole, a multiverse beyond imagining.